Hey guys, today we're going to learn about circuit diagrams. This is a circuit diagram, and I promise you the ones we're learning about are a lot simpler than this one. So to get there, we're going to start off by talking about schematics. And what a schematic is a stylized drawing, basically symbols on paper to describe circuits. So there's lots of schematic. This is a schematic diagram right here. And we're going to learn what some of the symbols are, just a few of them, just enough to do what we need to be able to do. Then we'll look at the two different types of electrical circuits, two basic categories of electrical circuits, and what's the same about them and what's different. And then we'll go into resistors in particular. Resistors have some little quirks about how they behave when you start grouping them together in different ways. So we'll look at that briefly. And then finally, we'll just get into some very simple circuit analysis, just to kind of get it started. Where we're going with this is next time on Friday, we'll have some more slightly more complicated circuit diagrams, and we'll look into the process of how we analyze those to figure out how much current is flowing through different things and how much power is being produced from where, that sort of thing. So circuit diagrams are very useful tools, and today is just an introduction to circuit diagrams as a thing. So let's start off with the schematics. So as I said, schematics symbols are stylized symbols that represent actual objects. As you can see, there's a whole bunch of weird little squiggles in here. We're only going to be using, I think, like one of these, maybe two of these in this entire diagram here. There are literally dozens, maybe hundreds of little things that you can put in circuits, and they each have their own symbol. We're only concerned with maybe a half a dozen of them, but like I say, it's enough to get you used to the idea here. So schematic symbols. The wire is the simplest one, or a conductor. It's just a line. So a line on a circuit diagram represents a wire, where a wire is going. Now we often need a way to turn a circuit on or off, so a switch is good. So the way we represent that is with a wire that ends at a point, and then it continues on over here. And if we draw it like this, this means that the circuit is open, the switch is open, meaning that electricity cannot flow through it because there's not a continuous wire. So an open switch or an open circuit is one where current does not exist, where electrons cannot flow. And sometimes that terminology confuses students a little bit, but we kind of think of it as a gate. It looks like an open gate. And when the gate is open, the fence is no longer continuous. The wire is no longer continuous, which means electricity cannot flow through that wire. So an open circuit, no current. And then we can also have a closed circuit, which looks the same, except that the line goes all the way through. So this is a closed switch, closed, and we do have current. Current does flow. Okay? Open switches and closed switches. Now the next thing is a battery. We got to have some way to power this thing. So a battery looks like this, and it has a short line and a long line, and a short line and a long line. That will be the easiest, and then it continues on this way. Okay, so yeah, this is a battery. Now, it doesn't matter to us which is the positive terminal and which is the negative terminal. It doesn't matter to us in AP1, but when you get to AP2, it does matter sometimes. So this is kind of trivia for us, but still. This is the negative terminal, and this is the positive terminal. And the way you remember is, see, it goes short line, long line, short line, long line. The short line looks like a minus, so that's the negative terminal. And then the long one is the positive terminal. Now, one more thing, because you may see this in different ways. The actual schematic for a battery, the simplest one is a short line and a long line, and that's it. And that's actually the schematic for battery. But batteries are often constructed with many cells that are stacked on each other to increase the voltage. So the way I've drawn it here, it's a little battery stacked up right next to another little battery. And it would be proper to, yeah, I have room down here, we can see it, to do short, long, short, long, short, long, and so on. You could do as many terminals as you want, as many cells as you want. It's just basically a stack of batteries. That's what it comes down to. So anyway, this is the most common version of it, and that's the symbol for a battery. Next, we have a resistor. Now, a resistor is a device that resists the flow of electricity, something other than a copper wire, something that electricity will have trouble getting through. And the symbol for a resistor looks kind of like a lightning bolt. It's a zigzag line like this. And it doesn't matter how many up and downs there are, you got to have at least two or three so it's clear that it's a resistor. But that's it. Now, very often we will write in the value of the resistor. So, like if this was a 3 ohm resistor, we would write 3 ohms above that to represent what it is. Same thing with the battery. If this is a 12-volt battery, we'd write 12 volts above it, and that represents the voltage of the battery, and so on. So a resistor is a squiggly line. Now, a light bulb technically is just a resistor, but since they glow with light instead of just getting warm, we have different symbols for them. But there's a couple different ways you can do it. One is just to make a little resistor with a circle around it. That's a light bulb. Sometimes you also see them as it goes up, and then it's a resistor, and then it comes down. So it looks like an old-fashioned light bulb filament, and then again, there's a circle around it. So it looks a little bit like a light bulb. The circuits that we're going to be working with for the most part in this unit, we'll just be using resistors, but sometimes it is useful to think of a resistor as a light bulb because you know that that's emitting energy into the room. It's emitting light. Energy is leaving the thing. It's warm. It's going to emit heat into the surroundings. So resistors and light bulbs. Okay, now sometimes wires are connected to each other. So if we draw them like this, that's ambiguous. You don't know if those wires are actually electrically connected to each other or if they're just stacked one on top of each other. You can't tell. So if we put a dot on it, that means that they are connected. Okay, that dot means that everything that goes into that point is electrically soldered together or welded together. Now, if we want to do wires that are crossing, but they're not actually connected, then we'll put a little U in like that so that let's move the arrow, so that you can see that the wire is passing over it and there's no electrical connection between those two. Again, these don't come up very often in the diagrams that we're going to be using, but they're so common that we may as well use them. Okay, I think that that's all we need. If you haven't already, pause it and write these down so you have them all in one place. The really important ones are this and this. Okay, and I think the wire is pretty intuitive. I guess the switch is kind of significant too. We have switches in there, but that's how it is. Okay, that's schematic symbols. Now, how do we put these things together into diagrams? Well, you know what? I think I have it in the slide deck. So let's just go to this. So here's one. So here we have, what is this? This is a battery, and it's connected to some wires. And these are two resistors here, which are connected to the battery. So the electricity can leave the battery, flow through these resistors, and then come back to the battery again. Now, most of you are aware that for electricity to flow through a circuit, you must have what's called a complete circuit. There must be a complete uninterrupted path from the battery or from the power source through whatever components you have in the circuit and then back to the battery again. Now, this one over here, we have a battery and a couple of resistors. Here we have a switch, and the switch is open. And because the switch is open, there's not this continuous path from the battery back to the battery. We don't have a complete circuit, so electricity will not flow in this circuit. This one, we do have a complete circuit, so electricity can flow in. Anyway, yeah, so battery, resistor, here's a switch, wires connecting them all, battery, resistor, wires connecting them all. This also brings us, though, to the two different types of circuit, two broad categories of circuits, okay? Because this one is really not the same as this one. And it's not just because this is an open circuit and a closed circuit, okay? Just bigger than that. This one on the left is called a parallel circuit. Okay, a parallel circuit. And in a parallel circuit, you have more than one possible path for charge or electrons to take as they travel through the circuit. So this is parallel because an electron can leave the battery and it gets to this branch here, and the electron could go through this one and then back to the battery. Or it could go over this way and go through this resistor, and then it's going to come back to the battery. So there's two possible paths, more than one possible path for the electrons to take. They call it parallel because these components are usually drawn parallel to each other like rungs of a ladder. Okay. Now, in reality, they don't have to be physically built that way. It's just that that's the way the electrical circuit is designed. So multiple paths is a parallel circuit. Now, the other type, which is this one over here, is a series circuit. Let's just go over here. This will be fine. So this is a series circuit, and in a series circuit, there's only one possible path for the current to follow. So an electron that leaves the battery goes through this resistor, and then it has to go through this resistor. It's the only way, and then when we close the switch, it will go back to the battery again. So there's only one possible path. So we call this series because the electrical components in the circuit are set up one after another. And you have to go through them in a series. First you go through this one, then you go through this one, then you go through the switch, then you go back to the battery. Everything is in series, one possible path. And the way we analyze these circuits is different, and we're going to see that more tomorrow because there are some characteristics of series circuits that are different than parallel and vice versa. Some things that these do that these don't. Some things that these do that these don't. And there's strategies that we can use to analyze what's actually happening. Okay, so series versus parallel circuits. Let's see, let's go on to the, we said we wanted to get to how resistors behave in groups, and this is really a good time to do this. Okay, so we have our series circuit here. And the question is, if you start stacking resistors in series, well, what does that do to the total resistance of the circuit? Suppose we have a resistor. This is a little piece of cardboard, right? And cardboard doesn't conduct electricity very well. So yeah, it's a resistor. And let's say it's 100 ohms. I'm sure it's much, much more than that because cardboard doesn't conduct electricity very well. But just for the sake of discussion, let's pretend this is a 100 ohm resistor. So if we have wires connected to this, and there's a battery over here someplace with the wires connected to the battery, the electrons have easy going through this wire, and then they hit this cardboard, and it's hard to force their way through it. There's a lot of resistance, and they force their way, and they finally get to the end, and they face 100 ohms of resistance. And then it's easy sailing through the wire again, and they continue on wherever they're going. Okay, great. So 100 ohms of resistance that it's dealing with. Well, what if we cut this resistor in half? All right. All right. And we now connect them with a wire. Well, each half that we have is half of the distance for the electrons to force their way through. So when they were together, it was 100 ohms. And even if we stick them back together after cutting them, it still is going to be 100 ohms of resistance, that much cardboard that the electrons have to force their way through. But if we separate them, well, I did do that right. Very good. Each piece has 50 ohms of resistance. Okay, so now if we set it up with a wire carrying electricity, well, now it's got cardboard. It's got to fight its way through 50 ohms worth of resistance. And then, hey, smooth sailing again because it's a nice clean copper wire. Oh, now we have to fight our way through another 50 ohms of resistance. So it doesn't matter whether the two resistors are actually part of the same physical piece or if we break them apart and move them apart. It's still a total of 100 ohms of resistance that electrons have to fight their way through. So what this means is that when we have resistors in series, we can just add up the individual values. I will make a drawing of this because it's better. So say we have a battery and a resistor and another resistor and back to the battery. If this is 10 ohms and this is 5 ohms, then the electrons, the battery is facing 15 ohms of resistance. So you can just add together resistors in series. Now, what if we have a parallel circuit? What if we take these same two resistors and we put them in parallel with each other? We call this one 10 ohms and this one 5 ohms. Okay. Well, now the electrons have a choice. If they go through the 10 ohm resistor, they will never go through the 5 ohm resistor because the electrons will flow kind of clockwise in this diagram. And an electron, if it makes it through this one, will never go swim upstream and go backwards through the other resistor. An electron will only go back toward the battery, right? It'll go like this. Electrons will either take this corner and go through the resistor, or they'll go straight and they'll go through the other one. But the flow is always kind of going around and around like this. Okay, so this means that in a parallel circuit, we do not just add them together. The way we actually do it is we treat them as their own individual little circuits. Okay, as far as this resistor is concerned, it's connected directly to the battery. There is a direct path from the battery through the resistor and back to the battery again. And it doesn't know or care that there's another resistor over here. It has nothing to do with the current flowing around this loop here. Okay, so that means that you can analyze this circuit as if it were the only game in town. And what we'll see is in just a moment here is that we can figure out how much current is flowing through this resistor if we know the voltage of the battery. The way we're going to do this is we're going to use Ohm's law. V equals IR, or I equals V over R, but this is the most common way that it's written. And we want to know the current. We want to know the current that is flowing through this resistor. So some current is coming out through the battery. It's flowing through this and then going back to the battery. Well, we know the voltage that's across this resistor because it's the only thing there. And we know the resistance. So we can say 2 volts is equal to the current, that's what we're trying to find, times 10 ohms. V equals IR. And so we divide both sides by 10, and we get 0.2 amps is the current. That's it. That's all there is to it. All right, now at the same time, we can do the same thing for the other resistor because this resistor has no awareness or concern with this one. I'm just going to kind of cover that up with the cardboard here so we don't see it anymore. As far as this resistor is concerned, the 5 ohm resistor, it's connected directly to the battery. It's the only thing that is soaking up that voltage. So we have a 2-volt battery driving a 5 ohm resistor, like a 5 ohm light bulb. So we do the same thing. 2 volts is equal to some current times 5 ohms. Divide both sides by 5, and we get, what is that? 0.4 amps is equal to the current flowing through this resistor right here. All right. Now, what that means is we have, in this diagram here, we have 0.2 amps running through this resistor and 0.4 amps running through this one. And all that current has to come from the same battery. So that means that there is 0.6 amps running through the wires right here, 0.6 amps running through the battery. That's actually more what we're going to be doing tomorrow, but it makes sense. Okay, so resistors in parallel, you treat them individually as if the other one wasn't there. And then resistors in series, you just add them together. So if we want to know how much current is flowing through this circuit, we add them together because the current faces 10 ohms and then 5 more ohms for a total of 15 ohms. All right, and let's say this is a 10-volt battery. We do the same thing. Let's do I equals V over R this time because why not? Works out the same way. We get 10 volts divided by 15 ohms, and that comes out to be whatever 10 divided by 15 is, 0.667 amps. So yeah, that's how you do these basic circuits. So the worksheet that you're going to have looks like this. I hope you can print out a copy of it. Ohm's law is printed up here for you for easy reference so you can remember. Let's focus this again because it seems to be a little bit blurry. Yeah, that's better. Okay, and all you're doing really is just applying Ohm's law to these very simple circuits. That's on the top half here. So it's the same sort of thing I was showing you before. 6 ohms with 12-volt battery, 5 ohms on, well, with 2 amps of current flowing through. You got to figure out the voltage of the battery and so on. That's what you're doing. Now this table here lets you try a lot of these. You get a lot of practice. And this diagram is just there in case it helps you visualize what's happening in the circuit. So for this top line here, we have 3 amps running through the circuit with a 5 ohm resistor, and you're supposed to figure out the battery voltage. Okay, and sometimes it's useful to visualize, okay, 5 ohms here, just like we wrote 5 ohms here. So that's just to help you visualize it if it's necessary. Now there's also a column over here for the power, and for power you use P equals IV. That was introduced last time, the power equation. So you can figure out the power that is being dissipated by the resistors in this. So let's go back to, this one right here. So suppose we have this one we just figured out that is 0.667 amps, so we're going to assume that that's true, and 10 volts is driving it. So to figure out the power for this one, we do P equals IV, which equals 0.667 amps times the 10 volts, which is 6.7 watts of power. So if this was a light bulb, or if these were light bulbs, they would be putting out a total of 6.7 watts. Great. So what we've done is we have introduced the concept of circuit diagrams in general and schematics specifically. Taught you the ones that you need for the ones that we're going to be doing. We talked about the 2 types of electrical circuits, parallel and series. We've seen how resistors behave when they're connected in series and how they can behave when they're in parallel with each other. And we will have more on resistors in parallel next time. There's actually an equation that you can use to figure out the equivalent resistance, but we'll get to that next time. It's not very complicated. And then we got to dip our toe in the world of circuit analysis. Anyway, I hope you found this interesting and useful and helpful, and we will see you next time.